All right, so in this module, we're going to talk about the second stage of annealing recrystallization. Okay, so I mentioned previously in the previous module, recrystallization, we're forming a new set of what we call strain-free grains. I do want to make a slight amendment here. So in the book and here it says strain-free. That's a little misleading. It's not 100% strain free, right? That means essentially we have a perfect crystal. There are still dislocations, but they're at a much smaller level. So they're basically at the pre-cold worked level. So that's just a slight iteration, but they're very low strain grains. And so the reason this occurs is because these new grains will have a very low dislocation density. That means that the strain energy is decreased. They'll also start being smaller in size. So this is before recrystallization. And then here's like on the right at the onset, you can see all of these little patches here. Those are new grains forming, like here, and you can see they're very small. And so the idea here is that they consume and replace the cold work grain. So the cold work has heavily been cold worked and strained, and therefore it's very high energy state. And so by replacing them with these strain-free grains, we are removing that. And that's what we're going to get to in the next part, which is the driving force. So the driving force is the difference between the internal energy of the strained and the unstrained material. So that's the driving force. So the more heavily cold worked it is, the more driving force there will be for it to form new grains. All right. And so during this recrystallization process, as long as it's at that temperature, it will continue to go until it's been consumed, right? So you'll form more and more new grains, and those grains can actually grow as well. But you tend to get a lot of very small grains and they consume. So here you can see they have continued to grow and you've continued to nucleate more grains. And then eventually they've consumed and you no longer see the original kind of structure that was there before. And so that's the process, and it's the driving here is to remove that strain energy for this process. And these new grains, although they're smaller, they have very little strain, and the dislocation density is going to be drastically lowered too. All right, so typically in the literature and in resources, you'll see what's known as the recrystallization temperature, or T sub R. This is the temperature at which 100% recrystallization has occurred in 1 hour. So if we look at the process here, in this case, it shows kind of the structure here. These are the cold work grains. They've been elongated, and then you see that you're starting to form new grains, right? And so this is basically the end of recrystallization when all of those new grains have taken over. And so you can kind of visually inspect this point by where the curves level out. So the strength has basically leveled out. The ductility has leveled out to its pre-cold worked level. And so this is basically the temperature then. So this is around 900 or so Fahrenheit in this case, or 500 degrees down here. And again, that's how long it takes, or the temperature it takes to recrystallize 100%. So we're talking about complete consumption of those prior grains in 1 hour. So that's the temperature that's often cited. I will say that we'll talk about this temperature isn't a fixed quantity, and we'll talk about what changes it. But for the most part, we can actually estimate where this temperature will be based on the material's melting temperature. So it tends to be between 0.6 and 0.3 of the melting temperature for that material. So that's always a first guess, even though that's a pretty wide range of materials and of temperatures. And the reason why this is varies so much is because it depends on a couple of factors. Because again, the amount of cold work is actually the driving force. So if we have more and more cold work, the recrystallization temperature actually decreases with that increasing cold work. So you can vary that crystallization temperature by varying the percent cold work. So it's not a fixed quantity. and also the purity of the metal. If you have a very pure metal, then the material tends to be low, and then the recrystallization decreases. If you add more and more impurities, the recrystallization temperature goes up. So basically, TR decreases with increasing purity. That's the way they're phrasing it. But essentially, impurity has a huge effect on the recrystallization. So we can't say that there's specifically one temperature because it varies depending on these factors. And so again, because the driving force is that recrystallization, and so and also the why the purity matters, you can kind of think of diffusion from a pure metal versus an alloy, right? We talked about solid solution strengthening, so those impurities tend to have different effects than the host metal. All right, so this is kind of the effect that we see. So here is cold work on the x-axis, and then recrystallization temperature on the y-axis, so that we see that with a very low amount of cold work, the recrystallization temperature is really high, and it actually kind of approaches an absolute value here. It asymptotically goes up, and that's because we think of a critical deformation. So below this amount, really you wouldn't expect recrystallization because there's not enough disorder or strain to actually undergo the recrystallization process. So you have to reach this point, and in this alloy it's about 5%, but it can be varied. And then beyond that point, though, the recrystallization temperature starts out really high for the low cold work and decreases the temperature as you go up in cold work, because again the driving force is greater with the increased cold work, and so recrystallization will happen at lower time or lower temperatures, but also in less time as well. So that's because of the driving force. And purity wise, we can kind of take a look at table 8.2 in the text, and we can look at copper, which is, again, in this case, it's very, very pure. You think of it as 5 nines, so very low amounts of actual other stuff. And then you can look at brass, which is 40% other stuff, in this case, zinc. And so you can see the recrystallization temperature for pure copper is 120, so very low temperature. And then as you start to add more and more stuff, the recrystallization temperature shoots up to 475 for brass. So it goes up. And again, it's related to that solute strengthening, because those solute atoms tend to segregate to dislocations and cause them to solute atoms can segregate to the grain boundaries as well and impede grain boundary motion, just like they did with dislocation motion. So similar process to that. All right, so before we end the module, I want to ask you one question, which will be on the quiz. With what we've talked about with annealing so far, and what you may just know in general about a material, let's envision that we have a material with a very large grain size, and we want to refine that grain size. And when we talk about refining, we're talking about decreasing the grain size. So see if you can think of a process by which you could refine the grain size. So think about that for a second. Think about what we've talked about. That might help, but you can also think about other options too. And then we will go do that on the quiz and come back and we'll discuss this. All right, so one process, which we've actually already talked about here, where we could refine the grain structure, would be to actually go through cold working and annealing, right? So let's envision that you have a really large grain size in your material. So let's say that we go through the process and we cold work it. So we have the cold work here, right? And so that's a similar process here. So it's been cold worked, those very large grains. And then what we do is we anneal it for a very short amount of time so that we get much smaller recrystallized grains, right? That's one way we could actually refine the grain size. So if we only anneal it for a short time before the grains continue to grow, where we just have these small grains, then we're able to refine or decrease the grain size. So that's one way. There's other ways we can refine the grain structure, but cold working and annealing at the right combination of time and temperature can also be used for that purpose. So that's kind of what I wanted you to think about. It's a tool. Cold working and annealing could be a tool for refining the grain size.